When two carts collide with each other, in this example, we'll imagine a red cart moving to the right, colliding with a blue cart that's stationary. And when the two carts collide, something special happens regarding the center of mass of the system. So if the two carts are of equal mass, then their center of mass is exactly halfway between the two. And in this example, the center of mass would then move with half the speed of the red wagon. So we can say, for example, the red wagon is going at a speed of 10 meters per second. Then the center of mass would be moving with a speed of 5 meters per second. And that's all assuming, like we said, that block number 2 has an initial velocity equal to 0. So I want you to watch a video that shows exactly what happens to that dot that represents the center of mass of the system as the object moves to the right and the collision takes place. So here's a simulation that shows how the center of mass of two objects moves in a collision. You notice the red cart comes in, collides with the blue cart, and there's a little dot between the two, and that dot represents the center of mass. You can see that the center of mass, if we replay it, is always located exactly halfway between the two objects because the two objects are of equal mass in this example. Wagon number 1 has a mass of 0.5 kilogram and wagon 2 has a mass of 0.5 kilogram. So notice that dot between them, they collide, and the dot continues moving at the same speed as if nothing ever happened. If we change the mass of wagon number 1 to be twice as large, so now it's 1 kilogram instead of a half a kilogram, then the center of mass is going to be located closer to the red wagon than the blue wagon, but notice the velocity of the center of mass. It stays the same both before and after the collision. So it seems that the velocity of the center of mass of any system stays constant when we compare before versus after the collision. So it's important for us to be able to calculate the center of mass for any system. So think of the center of mass of any system of objects as a weighted average. If I happen to have 3 objects, object number 1, object number 2, and object number 3, all located on the x-axis, then we can make up some values. We can say object number 1 has a mass of 5 kilograms, object number 2 has a mass of 3 kilograms, and object number 3 has a mass of 10 kilogram. And the distance from the origin to mass number 2 is a distance of 6 meters, and the distance to object number 3 is 10 meters. Then where exactly is the center of mass of this system of 3 objects? It's obviously located somewhere along the x-axis. So we'll say the location of the center of mass on the x-axis is called x subscript cm. And all we have to do is multiply mass number 1 times its location plus mass number 2 times the location of object number 2 plus the mass of object number 3 times the location of object number 3, and then to make it a weighted average, we divide by the total mass of the whole system. So in this example, it would be 5 times 0 plus 3 times 6 plus 10 times 10, all divided by 18. So we get a total of 118 divided by 18, which gives us a value of 6.55 meters. So somewhere just barely to the right of the 3 kilogram object is the center of mass for this system. Let's do one more example regarding center of mass. You can see we've shown the Earth and the Moon, and you have to forgive me for this diagram. It's horribly out of scale. The radius of the Earth is about 6.4 times 10 to the 6th meters. That's the same thing as 6,400 kilometer, which is the same thing as roughly 4,000 miles. So from where you stand right now to the center of the Earth is about 4,000 miles. The distance between the Earth and the Moon is 60 times that value. So if we take the radius of the Earth and multiply it by 60, that's the distance from the Earth to the Moon, and clearly I have not drawn it to that scale. So the distance between the Earth and Moon, we can call that R subscript EM. If you multiply 6.4 times 10 to the 6th by 60, you get a number of about 384,400 kilometer, which is the same thing as 3.84 times 10 to the 1, 2, 3, 4, 5, plus 3 more powers of 10, because kilo, so 3.84 times 10 to the 8th meter. So the location of the center of mass, if we make an x and y axis, and we choose to put the Earth right at the origin, then the location of the center of mass of the Earth-Moon system is the mass of the Earth times the location of the Earth in our coordinate system, plus the mass of the Moon times the location of the Moon, divided by the mass of the Earth plus the mass of the Moon. So grab your calculators and see if we work this out correctly. The location for the center of mass is equal to 0 plus, well, I need to give you the mass of the Moon. The mass of the Moon is equal to 7.35 times 10 to the 22nd kilogram. And while I'm at it, I'll give you the mass of the Earth. The mass of the Earth is equal to approximately 6 times 10 to the 24th kilogram. So we need to multiply 7.35 times 10 to the 22nd by 3.84 times 10 to the 8th, and divide that by the sum of 6 times 10 to the 24th plus 7.35 times 10 to the 22nd. So the answer we get is 4.65 times 10 to the 6th meters. But you notice that's less than 6.4 times 10 to the 6 meters. In other words, the location of the center of mass of the Earth-Moon system is less than the radius of the Earth itself. So the center of mass for the Earth and the Moon is actually located somewhere inside of the Earth. And you might imagine that the Moon orbits in a circle around the Earth, and that the center of that circular motion is the center of the Earth itself. Actually, both the Earth and the Moon are simultaneously orbiting around their common center of mass. We can extend our study of center of mass to systems of objects that are located in 2 dimensions. So imagine we have a 2 kilogram object that's connected by a lightweight rod to a 3 kilogram object, and another lightweight rod connects the 2 kilogram object to a 4 kilogram object, and then the 4 kilogram object and the 3 kilogram object are also connected. So we make maybe like a wire frame in the shape of a right triangle with little weights at each of the vertices. Where's the center of mass of that entire system? Well, if you eyeball it, you would guess the center of mass is probably located somewhere around that X marks the spot. We'll see if we've got that right. What we'll do is treat motion on the, or not motion, center of mass on the x-axis as being independent of center of mass on the y-axis. So let's work it out. The center of mass along the x-axis, that should be equal to the mass of object 1 times its position on the x-axis plus the mass of object 2 times its position on the x-axis plus the mass of object number 3 times its position on the x-axis, divided by the total mass of the whole system, m1 plus m2 plus m3. So let's call the 2 kilogram object number 1, the 3 kilogram object number 2, and the 4 kilogram object is number 3. So if we stick with our notation, m1 times x1 gives us 2 times 0 plus m2 times x2 gives us 3 times 5, plus m3 times x3 gives us 4, also times 0. And then divided by the total mass of the entire system is 9. So we get 15 divided by 9, which gives us 1.67 meters as the location of the center of mass along the x-axis. Let's work out the location of the center of mass along the y-axis. Mass number 1 times y1 plus mass number 2 times y2 plus mass number 3 times y3 divided by the total mass of the whole system, which as we know is 9 kilograms. So this time we get 2 times 0 plus 3 times 0 plus 4 times 6, all divided by 9. This is 24 divided by 9, which gives us 2.67 meters. Two kilograms at the origin, 3 kilograms located 5 meters away, and 4 kilograms was located 6 meters away. So the location of the center of mass of this system was over 1.6 units and up 2.67 units. So the center of mass of our system is right there at X marks the spot.